This lecture is on Newton's method for finding roots or zeros of functions. So here we have a function and it has a root right around here. And so this is how it works graphically, then I'll derive a formula for you. So we first guess that the root's over here. And what we do is we take that first guess at x sub 1 and we find the y value and then we draw a tangent from there. And wherever the tangent hits the x-axis, that is our new guess. Then we go back up to the function and we draw a tangent line from there. And where that hits the x-axis, that is our new guess. And you can see we're getting closer now. And we go back up to the function again and we have another guess. And from that guess, we would once again draw a tangent line. So we have that new guess, we draw another tangent line. You can see we're getting closer and closer. Now there are some pitfalls and things that can go wrong, but in this case you can see that we start to approach closer and closer to the real root. So let's take a look now at a formula we can use. And you can see this is an iterative process. We use one guess and then another and another. And so here it is again, this idea that you go up to the function, you take a tangent line, then you go, maybe in this case we overshot it. We go down to the function, we take a tangent line, we're getting closer. So we start with this point slope form here. Y minus y1, which is f of x1, is equal to the slope, or the derivative at x1 times x minus x1. Okay, now we solve this for y. Now the thing is, we want y to be 0 because we're trying to get to the x-axis. So if y is equal to 0, then we solve this equation here for x. So we put a 0 here, and if you solve it, you get x is equal to x sub 1 minus f of x sub 1 over f prime of x sub 1. And what happens is you can make this now into something more general where basically our x sub 2 instead of x. So our next x value is x sub 2. So from this formula here from point slope, basically this gives us the new x value. And then we generalize it further to get the next x value. And finally you have this formula here that the next one, x sub n plus 1, is always the previous x sub n minus f of x sub n over f prime of x sub n. Okay, and you iterate to whatever desired accuracy you want. So the point is we're using these tangent lines, and we want y to be 0, and if y is 0, we get this equation here, and our new x value from this line is found from this formula here, and we just generalize it. Okay, here's an example. F of x equals x squared minus 5. Find the 0 greater than 0, and we're going to start off with some guess. So the answer is rad 5, but we'll choose something around 3. Okay, so the derivative is 2x. All right, so x sub 1 is 3. So therefore x sub 2 is, here's our formula, is x sub 1 minus f of x sub 1 over f prime of x sub 1. So 3 minus f of 3 over f prime of 3. You plug 3 in here, you plug 3 in here. You subtract it from 3, you get 7/3. Okay, next one. X sub 3. Now we put 7/3 in, so 7/3 minus f of 7/3 over f prime of 7/3. You get about 2.238. You plug that in, and we get about 2.236. So after only 4 iterations, we're already getting very close because the numbers aren't changing very much. Okay, now here are some possible problems we can have with Newton's method. Notice that there's derivative as in a denominator. Now one way we see that as a problem is, this is an example. We've started with this value, tangent line, we're getting all the way to here. But if I choose this first value to be near a place that has a horizontal tangent, well, I'm dividing by 0, and you can see that my tangent line goes way off into the distance, and so if you actually are flat, it's not going to work at all. So that's one way it can go wrong, is if you're at something flat, because you'll never come back and hit the function, and we see that again here because you'd be dividing by 0. Another special case where things can go wrong is this particular function x to the 1/3, where actually each time you do a tangent line you get farther and farther away rather than closer and closer. So there's a particular type where that happens, but usually the pitfall you'll see, rather than being a cyclical problem like this, will be that you're close to, you're at a flat tangent line. You're at a local min or a local max. Okay, another problem, then I'll show you how to use some calculator syntax with this. Here we have the formula again, Newton's method. This function, this is our first guess. Okay, so we need the derivative because we have to be able to plug into the derivative. And so x sub 2 is x sub 1 minus f of x sub 1 over f prime of x sub 1. So you plug these guys into the function and the derivative, do the arithmetic, and you get 3/4. 0.75, you plug that in. So the next value, plug in 0.75. You get all this, 0.686 approximately. You plug that in to everywhere, and you get down to here. And you can see that this number on top is getting smaller and smaller, which implies that we're getting closer and closer to our answer. Now let's take a look at some of the syntax you could use for the calculator to do this more efficiently. I'd want to see some work like this, but this is a quick way to do it. Here's your function, here's your derivative, and this is the initial guess. Okay, so what you do is you put in for y1 the function, you put in for y2 the derivative, so you have to figure that part out on your own. Okay, then we come over here to the main screen. All right, and what we want to do is now apply Newton's method. Okay, so our first guess was 1, so it's 1 minus y1 of 1 divided by y2 of 1 Okay, and this is going to give us our next value, and it's 0.75, which should be. And now what I do is instead of plugging in 0.75, I do second entry, and I go back, and wherever I had a 1, I put second answer. So it's going to use the previous answer. It'll use 0.75 and plug in 0.75. So second answer, second answer, second answer. So what this does is it will keep using the previous value, and so it does the iteration for you. So you press enter, there's the next one, just keep pressing enter. You just keep pressing it until eventually you can see we do about 5 iterations, and we're not changing to about 10 decimal places, so clearly we're coming in on the 0 very well here. So that's a quick way to do it with TI syntax. One other method for finding zeros, this is possibly more of the way your calculator might do it, is the bisection method. I'll just show you graphically what's going on here. With the bisection method, if you have a function like this, you choose a number to the left of where you think the 0 is. So we choose a number, say, over here. We'll choose one to the right. And you say, okay, the y value here is positive, here it's negative. They're different signs. And because they're different signs, I pick right in the middle. So I bisect it. And then this one here is positive. So now I use the positive and the negative, and I bisect those. So now I get maybe to this spot here, and that's negative. So then I bisect those, and that's positive, and I bisect those. So you always have to bisect with the opposite sign, of course, and that one is positive. I bisect again. You get closer and closer that way. So that's a different algorithm that's sometimes used for finding zeros.